So I wanted to talk about sedimentary rocks and processes just to be able to reconcile the things that you have already read in your module and emphasize certain things that may be new to you. So this is a picture of the Grand Canyon, which was shaped through weathering, erosion, transportation, deposition, and diagenesis. So we are going to look at each of these processes in this lecture. So the objective of this lecture is to define weathering, what are the agents of erosion, classify sedimentary rocks in a separate lecture. Then we're going to talk about sedimentary structures and perhaps resources from sedimentary rocks. So from here, we can see that you have uh, a rock, a pre-existing rock that is weathered, then eroded, which is taken out from its original position, transported and deposited in a separate or a different environment, and then eventually it will be compacted and cemented to form your sedimentary rocks. Okay, as I said, weathering, what are the two types of weathering? So you have physical weathering and chemical weathering. So the difference between them is in physical weathering, you have physical breakdown and disintegration. And for chemical weathering, there is chemical alteration that happens, which is also, it happens on the surface or at or near the surface where your minerals decompose. For mechanical weathering, you have a physical force of stress that is applied to the rock. And because of this, you break your rock into smaller pieces, which increases the surface area of your rock. Okay, and it's good to note that there is no accompanying change to the composition of your rock. So what the composition of your rock before is still the composition after. It's broken down into small. So here, for example, we have frost wedging, which is a type of mechanical weathering that has repeated cycles of freezing and thawing. So you have water that fills a crack in your rock, a pre-existing crack, and as it freezes, it expands, and the repeated expansion and contraction eventually leads to the breaking of your rock. Another type of mechanical weathering is heating and cooling. And because rocks are not good conductors of heat, they expand and contract, which eventually leads to cracks in your rocks. Wetting and drying is similar, but it happens in soil, where you have swelling and contracting of your soil particles, which eventually leads to that type of weathering. You also have, of course, biological weathering, where you have certain animals or plants that help in disintegrating your pre-existing rock. For unloading or unroofing, which is something that may be new to others in this class, you have, for example, an intrusion that has occurred sometime perhaps since there's a dinosaur here in the Cretaceous, and eventually this part is eroded, and because there is no overlying burden, there is no more balance in your pressure, and eventually exfoliation of your rock occurs. So looking at this in a real picture, you can see that some of these parts, some of the parts of your intrusion are sloughing off or are being exfoliated. Okay. You also have abrasion, where because you have moving particles, it starts to scrape off parts of your rock and abrades it. Okay. For chemical weathering, it's all about decomposition, as I said earlier, where you eventually produce soluble ions, clay minerals, and resistant minerals. In chemical weathering, you have common agents such as water, chemicals dissolved in the water, and gases in the air, which eventually, again, breaks down your rock components. Okay, so the goal for chemical weathering is to produce more stable minerals. An example of which is dissolution. So you have the incorporation of a solute in a solvent. For example, you have halite or rock salt, with the addition of water dissolves into your sodium and chloride ions. Okay, but not all minerals dissolve in water readily. So what about acidic water? Limestone and marble, which is CaCO3, in reaction to carbonic acid produces um, calcium ions and then your bicarbonate ion, which eventually becomes carbon dioxide and water. In hydrolysis, you have reaction with water to form hydroxides. These hydroxides are more soluble than your original mineral. So for example, the hydrolysis of potassium feldspar to clay. So you have potassium feldspar ions here, which react with carbonic acid to form clay. And clay is more stable and therefore the result of your chemical weathering. In acidification, you have acceleration of weathering by the presence of hydrogen, the hydrogen ion in water, which is provided by your carbonic and organic acids. Hydration, in contrast, is a combination of a solid mineral or element with water. In this case, anhydrite is transformed into gypsum. Interestingly, anhydrite has a hardness of 3.5, and as you add water to it and transform it into gypsum, gypsum's hardness is actually softer at hardness 2 on the Mohs scale. In oxidation, you have a gain of oxygen. In reduction, you have a loss of oxygen. So because of this gain or loss, you have a change in the oxidation number of an element, an example of which is iron, combination with oxygen to form hematite, which in this picture on the left, you can see that it has a reddish brown hue. And because of this, you can see like in desert landscapes, oxidation is a prevalent chemical type of weathering. In ion exchange, you have substitution in solution. So usually it's most effective in clay minerals. Okay. What are the factors that affect weathering? Okay. There is susceptibility of minerals to chemical weathering. The Golditch stability series describes the order in which silicate minerals weather. And if you look closely, it is similar to the Bowen's reaction series, but it is just flipped from olivine being at the top and quartz being at the bottom in the Bowen's reaction series. Here, quartz is at the top, which is more resistant to chemical weathering, and then olivine is actually less resistant to chemical weathering. So minerals that form at high temperatures and pressures are least stable on the surface and weather most quickly because they are farther from the zone of stability or the conditions at which they form. Okay, so some factors that affect weathering are climate, relief, rock type, time, and of course, organisms such as people, plants, and animals. For climate, as you increase precipitation, you affect the extent of hydrolysis and dissolution. In highly precipitated areas, you have chemical weathering that is dominant, especially in wet and humid areas, while in dry areas, mechanical weathering is most prevalent. Temperature fluctuations also affect frost wedging and heating and cooling. Relief refers to the steepness and exposure or the amount of the exposure of rocks on the surface. If you have steeper slopes, unstable grains are sloughed off and put here and then eventually are covered and preserved. In contrast to slopes that are more gentle, which are more exposed and therefore have higher rates of chemical weathering. For rock type, fine-grained rocks decompose chemically more readily than coarse-grained rocks due to the fact that it has more exposed surface area. Joints also play a role in increasing the surface area for chemical attack. Differential weathering also occurs when one rock is more susceptible to weathering than the other. As we see in this photo on the right, some rocks are jutting out because they are more competent, and then the others are softer and therefore more readily weathered than the competent rock. We call this an incompetent bed. Okay, so the less stable it is, the more it will weather first. As we weather certain rocks, we form soil profiles. But what is soil? Soil is actually composed of rock, air, water, and organic materials mixed together. They vary in color, texture, and mineral content. So there are orders or types of soil such as alphisols, aridisols, entesols, and so on and so forth. On the rock, you can see a map of soil. That is actually helpful for example, agriculture. So which soils are better for growing certain crops, etc. Okay. So what are the soil horizons or layers? Here we have O, A, E, B, C, and R horizons. The O horizon is your organic layer of soil made up mostly of leaf litter and humus. The A horizon is made up of humus, which is the decomposed organic matter. E is called the leaching layer or the eluviation layer, where water seeps through and removes ions as it drips through the soil. The B horizon contains clay and mineral deposits from this eluviation layer, and these deposits are iron, aluminum oxides, and calcium carbonate that receives from layers above it when water drips from the soil above. The C horizon consists of slightly broken up bedrock. Some plant roots do not penetrate into this layer because of very little organic material, while the R horizon is an unweathered rock layer. It's important to note that the more weathering that occurs, the more complete your soil horizons are. Let's move on to erosion. Erosion comes from the word meaning eat away. It involves the movement of rock or soil. What is it eaten away by? Okay, so we have the agents of erosion such as gravity, illustrated at the top portion, water, ice, organisms, and wind. As your material is being eaten away, it is readily now transported by your transporting agents. Your transporting agents have competence. Transporting agents have competence and capacity. Competence is the biggest size an agent can transport, while capacity is the maximum load of sediment an agent can transport. Okay, so similar to your agents of erosion, you have agents of sediment transport such as ice, water, wind. And when we say anthropogenic causes, we mean human intervention. There are several different ways on how sediment is transported. You can have movement in solution as suspended particles or as dissolved particles in solution. You can also have saltation, which is jumping, and you also have traction along the surface. Okay. Preventing erosion by using cover management, and in this case, a beach wall, prevents some of these materials from being transported, although it's not perfect solution. As your material is being transported, it can also be sorted. Sorting is the measure of variation of grain sizes, where you have a mixture of different grain sizes in poorly sorted sediments and more or less the same size sediments in well or very well sorted sediments. Generally, as you move further from the source, the more of your larger or coarser grains are left behind and eventually reach the same sizes. So here, for example, we have poorly sorted sediments where you have larger grains and smaller grains combined into one. And as you go to well-sorted sediments in longer distances, you have already sorted into a similar grain size. In terms of shape, roundness measures the angularity of corners, and generally, as you move further away from your source, the more rounded your materials become. In contrast to sphericity, which measures how closely the grain shape approximates the sphere. In this case, it depends on what environment you are depositing, where, for example, if you have wave action, it's more flattened. If you have river action, it's more spheroidal, and so on. Okay. This is mentioned in your module, the Uden-Wentworth scale, which is the measure of size classes based on the size of your grains. So the larger the grain sizes, the more negative the phi size, which is generated from this equation, where phi is equal to the negative log to the base 2 of the diameter or average diameter of your sediment. As we transport, eventually we lose energy and deposit. When transported material settles or comes to rest, it happens when an agent loses energy and can no longer transport its load. So generally, the grain size has a relationship with energy. The higher the grain size, the higher the energy for transportation, as we mentioned in the Holstrom-Sundborg diagram. As your sediments are deposited, eventually they will form into rock in a process called diagenesis, which includes all physical, chemical, and biological processes that take place after sediments are deposited. So you have sediments that transform into sedimentary rocks through the process of lithification, and it modifies the sediment's composition, texture, and structures. Generally, burial promotes diagenesis, which occurs at the upper few kilometers of the Earth's crust, at temperatures ranging from 150 degrees to 200 degrees Celsius, because beyond this, the process of metamorphism takes place. You have two types of diagenesis. Early diagenesis, which takes place at shallow depths, and you have late diagenesis, which is from deep burial to subsequent. What happens during diagenesis? You have compaction, which is the process by which the volume of a sediment is reduced as the grains are squeezed together due to overlying pressures. And these pressures remove fluid from your rock, which eventually compacts and lithifies your unconsolidated sediments into sedimentary rocks. Another diagenic process is called cementation, which is the precipitation of new minerals by organisms in the pore spaces between grains to form a cement. You can also form cement by precipitating insoluble ions from solution. The cement therefore becomes the glue that cements or glues rather your sediments into solid rock. Common cements include quartz, calcite, and hematite. Other diagenetic processes include recrystallization of unstable sediments, such as in aragonite, which is CaCO3, but calcite is more stable, but is also calcium carbonate. You also have dissolution and replacement of certain minerals, and you can also have bioturbation, which is the disturbance of your forming rock layers by organisms. Diagenic environments can influence the color of your rock. As I mentioned earlier, oxidizing environments can have rust-colored rocks. In contrast, reducing environments, since they have a high organic material content, produce dark-colored rocks. And this ends our review of the different processes of weathering, erosion, transportation, deposition, and diagenesis.